here talking with intro. So I'm going to be talking about some work that I did during my NCAR summer internship and it was essentially developing Jupyter book tutorials. Sorry, I'll introduce myself a little bit more. I'm a PhD student at the University of Utah currently. I'm in the geography department, and my research mostly focuses on glaciers in high mountain Asia and using a lot of remote sensing data to better understand recent variability in those glaciers. But today I'm going to be talking about developing Jupyter book tutorials demonstrating xarray-based workflows for cloud-hosted remote sensing data. And this was work that I did during a summer internship with the NCAR SciParks program. And I just want to take a moment to thank my internship mentors, Jessica Scheich, Scott Henderson, and Deepak Cherian for all of their guidance and support during this project. So I'm going to go through the background of this pretty quickly because I imagine I'm kind of preaching to the choir a little bit, but I'm happy to talk more about any specifics if there's interest. But just quickly, the data that I'll be talking about today is satellite remote sensing data, which is a really valuable tool for better understanding Earth's surface and the processes therein and our climate system as a whole. But as I'm sure a lot of people have experienced, the data sets can often be large and complex and somewhat unwieldy. And can be difficult to work with, which brings me to the main computational tool that I'm talking about today, which is xarray, the Python package for working with n-dimensional gridded data sets. It also has backend integration for various cloud-optimized data formats, which is really helpful for the computational setting in which this work takes place, which is the transition to open and cloud-based science. And just to talk about that a little bit more, the traditional kind of download model of computationally intensive workflows really ties ability to do that kind of work to access to significant computational resources. And that prohibits a lot of participation in this field and in this type of scientific research. Cloud computing resources can democratize scientific participation and reduce computational barriers to entry to this kind of work. But many recent papers about this transition note that it's more than a technological transition. It's also a product of norms, practices, and community behavior around that technology. And that it is important to deliberately design new community infrastructure. So kind of in the interest of community infrastructure, that really motivated this work toward developing educational resources for using xarray to work with satellite remote sensing imagery, and to hopefully increase the user base of both these data sets and these tools and make them more accessible overall. Just to kind of quickly go over the platforms, the cloud computing platforms and computational tools that I used during this work was Amazon Web Services, Microsoft Planetary Computer, Pangeo Jupyter Hub, Alaska Satellite Facilities On-Demand Processing Service, and then too many software packages to count, but just two of them being xarray for working with gridded data sets and Dask for parallelizing workflows. So I worked on two separate tutorials this summer or during this project, but I thought rather than, I didn't want to click around on a web page because I thought that'd be pretty boring. So I thought I would describe the two data sets that they individually focus on and why they were a good fit for working with xarray, and then talk a little bit about the approach that I used when I was developing the tutorials, and then reflect a little bit on what I learned. So the first tutorial focuses on the ItsLive dataset. ItsLive is a NASA measures project to provide automated low latency global glacier flow and elevation change datasets. And this is a multi-sensor data set with velocities derived from Landsat 7, 8, and 9, as well as Sentinel-1 and Sentinel-2. And the data is available in traditional data formats such as GeoTIFFs and NetCDF files, but it's particularly exciting that because it's also available as SAR data cubes that are hosted on AWS and available in S3 buckets. So making this huge amounts of data really easy to access and work with. And the snapshot here on the right is just to kind of show an image of what a single granule looks like and why xarray is a really great tool for working with this data. So this is one granule that's accessed from the S3 bucket. You can see that we have X, Y, and time dimensions, as well as 54 variables that exist along some or all of those dimensions. And so using xarray to work with this kind of data set really makes it much more intuitive and efficient, and kind of takes away a lot of the keeping track of that you'd have to do on your own. Having it in the xarray format and being able to leverage X-ray functionality is really nice for this data set. The second book focuses on Sentinel-1 RTC imagery. Sentinel-1 is a synthetic aperture radar that operates at C-band, and it's operated by the European Space Agency. Radiometric terrain correction is a correction process to prepare the SAR data for analysis, and it corrects for distortions that arise due to the interaction of the viewing geometry of the side-looking sensor and the surface topography of the field of view. And as someone, I've only done a small amount of like playing around with my own processing, and it's complex and it's computationally intensive, and it's really non-trivial processing step. So having data sets of data that has already undergone RTC processing publicly available, I think is really exciting for the community and really broadens the amount of work that can be used with the work that can use SAR data and the questions that we can ask of these data sets. So I'm focusing on two different RTC data sets. The first is processed by Alaska Satellite Facility's on-demand processing service, and then it is downloaded and worked with locally. The second is Microsoft Planetary Computers data set, and so it's processed and hosted by MS Planetary Computer, and it's stored as cloud-optimized geotiffs that adhere to stack specifications. So we can use tools like PyStack and StackStack to query and access this data. And just to talk about the approach that I used when working on these tutorials, and this came out from a lot of feedback and back and forth with my mentors, so it was really helpful working with them. And we really placed an emphasis on including narrative and explanatory text with accessible language and staying away from jargony terms. And then also linking to outside resources, whether they are documentation, other tutorials, or even particularly helpful Stack Overflow answers for certain tasks. Oftentimes these are resources that I found helpful while I was writing the notebook. And if I got confused on something, looked elsewhere, found something helpful, then I included it in the text. I also made an effort to keep errors in and not only show code that works, but also show code that, like this is the first way I thought to do this. This is the error I got. This is what that error message meant and how to move past it. So at a smaller scale, this looked like keeping in those errors. And at a larger scale, this ended up taking the form of even an entire notebook that we developed that was working, but ended up not being quite like the right approach and didn't really work at scale. But we decided to keep it in, and hopefully it's a valuable learning tool to someone later on, whether it's the syntax in there or even just like conceptually comparing the two approaches. For me, both of these were really valuable things to do because it kind of forced me to, rather than just get something working and move on, it forced me to actually make sure I understood why the code was working and what I had done to make it work after I changed it, and just have, I think, like a deeper understanding of really what was going on under the hood. So to talk a little bit just more specifically about that one example, because I think I learned this encapsulated a lot of like my experience working on this, which was, running into getting something working and then running into an unexpected error and having to dig a little deeper. So when I was first working on reading in the stack of ASF processed RTC imagery, I was excited to use Xarray's OpenMF dataset tool because it's a great tool for reading in a large stack of data, and you have so much degree of customization to structure the data and the metadata how you would like it to. But I ended up running into a lot of memory issues later on. So I was able to get it working. But then when I tried to kind of like proceed with that, I was running into memory issues, and it ultimately, and that was related to certain characteristics of the data set that made it difficult to find an appropriate chunking strategy, which I just kind of illustrated with this screenshot here. So various aspects of the data set made it difficult to chunk it in a good way for moving forward with it. And we ended up using instead GDAL virtual raster format objects. And this let us read the data in with a lot less computational expense, but the consequence at the expense of losing a lot of structure of the data that we got from the X-ray method and a lot of the metadata. So that created a lot of work on the back end, kind of structuring that data to prepare for analysis. But ultimately, it was kind of the way that we were able to get it to work and move forward with. But for me, this was an example of thinking I understood a tool and how to use it, but then having that not really quite work for me and having to go back in and become much more familiar with the tool and the data that I was trying to use the tool with. And ultimately, like, this ended up being that I didn't understand the tool as well as I should have going into it, and to know that this wasn't quite the appropriate situation to use it in. But it took me kind of running into that issue to figure that out. And so this was, I think, a really valuable learning experience for me, where I was using the tool in a situation where I needed to parallelize, whereas in the past I had maybe been doing it in a situation where I didn't need it as much. And that helped me learn a lot more about the tools that I was using, the situations I was trying to use them in, and really, like, ultimately the best way to orient my workflows toward using these tools. So that was just kind of one example of something that was a valuable learning experience for me during this project. And to just, I guess a little bit more in general, other things that I learned working on this project were I got a lot of experience working with collaborative workflows and version control and interacting on GitHub. And then also writing better and more efficient code rather than just kind of getting something that worked and moving on. Having the time to go back and improve upon something was a really valuable learning experience, as was kind of doing the same thing with parallelizing workflows. Working with cloud computing resources and cloud optimized data formats was all new to me and came with kind of a new set of terms and tools that it was really exciting to start playing around with these tools. And it's something that I'm excited to continue doing in the future. And then more generally, I think this kind of, I'd been a longtime lurker in this space and others, but this was maybe an introduction for me to the open source scientific software community. And it really broadened my understanding of all of the work being done, all of the different types of work being done in this community, which was a really valuable learning experience, but also kind of left me excited and like with ideas of new ways that I could see myself being involved in, which I hadn't really understood in the future. So that was really positive, and also I should say just a ton of fun. So I want to thank my internship mentors again, Deepak, Scott, Jessica. One of my academic advisors also spent some time with me on this book, and then also the NCAR SciParks program for all of the support this summer. These are my references, and I'd be happy to take any questions.
Awesome. Thank you so much. See some applause.